Have you ever stopped to think about your phone charger? I mean, really think about it? Remember those giant, heavy power bricks we used to have for old laptops? The ones that felt like they weighed more than the computer and could probably heat a small room. And now, look at the charger for your phone. It's tiny, it's light, and it barely gets warm. So what on earth happened? How did we manage to shrink our power supplies down to almost nothing while making them way more powerful? Well, the secret is a really clever trick that involves turning power on and off thousands and thousands of times a second.
All right, let's dive in. Here's our roadmap for this explainer. We're going to start with the power supply revolution, then uncover the secret of switching. After that, we'll look at the smart feedback loop that makes it all work, decode the language of pulses, and finally see why all this efficiency is such a massive payoff. And, what happens when it all goes wrong.
So, at the very heart of this huge change are two totally different ways of thinking about power. You've got the old school heavyweight champion, the linear power supply, and then you have the modern, super nimble contender that's in pretty much everything we own today, the switch mode power supply, or SMPS for short. And when you put them side by side, the difference is just staggering. I mean, look at these numbers. An old linear supply literally wasted about 30% of its energy just as heat. That's why they were so big and heavy and hot. A modern switch mode supply, on the other hand, is up to 95% efficient. That huge leap in efficiency is what makes all of our small, powerful devices even possible. So, how does an SMPS actually pull this off? Well, the secret isn't about providing a nice, constant, steady stream of power like you might think. No, the real magic is in turning the power on and off at an incredibly high frequency. It's a process we call switching. So here's the basic idea. You've got a control chip that acts like a lightning-fast switch. It creates these tiny pulses of power that drive a special kind of transformer. And it's that rapid pulsing that induces a voltage on the other side and lets the energy transfer across. And get this, if you just fed a steady current through it, absolutely nothing would happen. The whole secret is in that constant on-off change. But this high-speed switching isn't just random chaos. It's actually incredibly precise. The power supply is having this constant, intelligent conversation with itself to make sure the voltage coming out is perfectly stable, no matter what you're doing. And it does this using something called a feedback loop. You know what this is like? It's exactly like the thermostat in your house. It's always checking the room temperature. That's the output. And then it tells the furnace when to turn on or off to keep that temperature just right. The power supply is doing the exact same thing, just thousands and thousands of times every single second. And this is where the design gets really, really brilliant. See, the high voltage side of the circuit needs to talk to the low voltage side, but you can't have a direct electrical connection. That would be incredibly dangerous. So, how do they do it? They send the signal using a tiny beam of light inside a component called a photocoupler. It's like sending Morse code with a tiny flashlight, creating a perfect electrical barrier that keeps both you and your device completely safe. Okay, so we have a switch turning on and off like crazy, and it's being controlled by a feedback loop. But what language is that loop using to tell the switch exactly what to do? The answer is a really cool technique called pulse width modulation, or PWM. The key thing to understand here is the duty cycle, which is really just a fancy way of saying the percentage of time the switch is on versus off. Honestly, the best analogy is the gas pedal in your car. When you need more power to get up a hill, you press the pedal down for longer. When you're just cruising on a flat road, you ease off. PWM is doing the exact same thing, but with tiny pulses of electricity. And this is what that looks like in the real world. Think about your TV when it's just in standby mode, with the little red light on. It doesn't need much power at all. So the control chip tells the switch, hey, just use a really low duty cycle, maybe 20% on time. But the second you hit that power button and the screen flares to life, the feedback loop senses that huge demand, and it instantly tells the switch to crank the duty cycle way up to 80 or 90% to deliver all the power it needs. So this ability to perfectly match the power output to whatever the device needs at any given moment, that is what makes these power supplies so incredibly efficient. And that efficiency has completely changed the world of electronics. Because it's only working as hard as it absolutely needs to, an SMPS converts nearly all the electricity from the wall into useful power. That means very, very little energy is wasted as heat. Now compare that to the old linear supplies. They were basically fully on all the time, and they would just burn off any power they didn't need as heat. That 30% waste is why they were so massive and got so hot. It was pure inefficiency that you could literally feel. And this right here is the real payoff. This incredible efficiency is the direct reason our gadgets are smaller and lighter, why they're more affordable to make, and why they save us energy over their lifetime. It is truly the unsung hero inside every single piece of modern tech that we own. All right, so now that we know how these little marvels of engineering work, we can also get a pretty good idea of what happens when they break. And this knowledge can be a surprisingly useful tool for anybody who likes to tinker or repair their own stuff. So when a device just won't turn on, it's really easy to assume the most complicated part has failed, right? Like the control chip or the main transformer. But you know what? That's almost never the case. In fact, the transformer itself is incredibly tough and hardly ever breaks. The real culprits are usually much, much simpler components. So if you ever find yourself troubleshooting a dead power supply, these simple components are your prime suspects. Capacitors are public enemy number one. They work really hard filtering the power, and over time, they just wear out. They can bulge or even leak. But they're not the only ones. Diodes on the output side and the little protection circuits can also fail under stress. A lot of the time, you can spot the problem just by looking. This whole principle of intelligent, high-speed power control is really the foundation of modern electronics, and it is not standing still. Engineers are pushing switching speeds even higher and making the control systems even smarter. It really makes you wonder, if we went from a literal brick to a tiny cube in the last 20 years, what on earth is the charger on your desk going to look like in the next 10?